connecting to the cloud. Ladies and gentlemen, welcome to Dark Matter Day.
We should still take notes, right?
If it were me, I would. It's your parents' tuition dollars at work. It's insanely cool. It's not going to be on anybody's AP exam because the AP tends to be at least 50 years behind the times, if not positively 100. All right, morning warm up. This is why we did the centripetal force last week. This was the point of it all. You won't need your calculator because we don't have any numbers, but here are the equations we've been playing with in the land of old-fashioned Newtonian forces. You have a star of mass m. It's going round and round the galaxy. Galaxies spin. The galaxy has a massive big M. What's keeping it there? Gravity. Which way is gravity going? Clearly, it's going toward the center of the spiral because the galaxy is moving round and round in circular motion. Find the speed you need to maintain that motion. Hint, if gravity is the centripetal force, this ought not to be too bad. Pick up those pencils, deploy some algebra.
Yeah.
Matan, which of those pesky letters canceled out?
Mass.
Oh, which mass? The big mass or the little mass? Okay, so you don't need to know the star's mass. You don't need to know anything's mass in order to know whether or not it's going to continue in orbit. Jonah, what did you get for orbit speed? Okay, so what do you need to know in order to find or measure the velocity of a star according to your formula? What do you need to know?
The distance from the star to the center of the galaxy.
Okay, you need to know the distance from whatever it is to the center of whatever arc it's making. In this case, the distance of whatever star you happen to be working on to the center of the galaxy. What else do you need?
What the equation was?
Yes.
Oh, there
Label it orbit speed and put a box around it. This is the necessary precondition for launching something into orbit. This math is infallible, was an if-then logical construct. It's 400 years old. Newton figured out how fast you needed to launch something in order to put things into orbit. It's the only thing he didn't have was the actual number for G, which wasn't measured until the 1700s when Cavendish picked up where Newton left off and managed to actually get some data. That's how fast things in space are traveling. How do we know? Because they're moving in circles. They wouldn't be moving in circles if this weren't true.
is G a constant?
Yes, G is the universal gravitational constant. Today would be a good day to write it down if you haven't done so already. G is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. And if you want to see a diagram of Cavendish's experiment and how he measured such an insanely small number, go to the gravity and outer space section of the class YouTube channel and watch Newtonian gravity part 1, the first in the series. Eliana.
What's on the denominator?
Newton meters squared per kilogram squared. Sure. Good question. Other questions about orbit speed, how we know it to be true. If you're not going this fast, you will, how you say, fall down, go plop. In the small scale here in the world, we call it gravity. On the large scale, if you're a rocket or a plane or something, we'd call that a crash. It's where you fall down and meet the floor. Question.
So you said that's the speed needed to launch something into orbit.
Yes.
Are you when you're calculating that, do you measure like in terms of launching something into orbit out of like Earth's atmosphere?
Then you'll need to know the mass of the Earth, which by the way is 5.98 times 10 to the 24th kilograms. And you'll need to know R, the distance from you, watch, to the center of the Earth, not the outer edge. When we
like
do.
From you, so from the center of the Earth to like the outer edge of the orbit?
Yes, what would you call that if you were trying to launch into orbit virtually at ground level? The distance from the center of the Earth out to you, what would you call that? It's weird to think about it. Let's draw a picture. Here's the Earth. You want to orbit it. If it weren't Earth, if it were some other planet that doesn't have a pesky atmosphere in the way, also trees, mountains, etc. If you just wanted to go into orbit, this would be you. Chapter 8 will learn about the center of mass and why physics always goes from center to center. What would you call this on the planet if you were basically just above the surface? What do we call that part of the circle? Yeah, it would be the radius of the planet. Now, given that this is Earth and there are mountains and trees and there's 100 kilometers of atmosphere that we call the Kármán line, the cat in the hat wants to know how high is the top of the sky. Oh, I got that one, 100 kilometers. After the 100 kilometers, the oxygen has run out and what's around you is no longer blue because of the red lines and the orange lines in the absorption spectrum. It's black because space. So if you've got an orbit height of 8, the denominator here would be the radius of the planet plus h, distance from center to center. Good question. Other questions?
Isn't it also possible to go too fast to fall into orbit?
Yes, we'll do that when we do conservation of energy next. All right, any questions about the land of V equals? All right, now that you've got all this experience, calculate the mass of a galaxy rotating with period T. Why? Because we watched the stars going around the heavens for long enough. We said, hey, that star is right back where it was my first year in graduate school. It must have completed a full period. Those of you who've done this before and didn't simplify the first time, simplify now. Ought to be a real efficient calculation because it's review. Take it away.
So Eliezer, if we measure a period of another planet,
Yes.
would we even be able to?
Sure, just
Okay.
watch it for long enough. If it's really, really, really slow and really, really far away, you may have to access the astronomical data of ages past. Fortunately, we have close to 3,000 years of astronomical data because the Chinese emperors ruled by the mandate of heaven. And therefore, since the founding of China as an imperial power, long before the Common Era, that every Chinese emperor who wanted to hold his throne maintained a professional college of astronomers whose job it was to watch the sky all night long and take excellent notes, because if the mandate of heaven was withdrawn and the stars said your dynasty was over, the emperor wanted to see if there was anything to do he could do to fix that, or failing that, to know where the emergency exit was, and a couple of rollers to smuggle out his family and several crates of gold bullion to start a new life in Mongolia. So the fact that the Romans took excellent notes, the Romans were Johnny come lately. Yeah, I know Ptolemy was really big into astronomy, but the Chinese had him beat before his great-great-grandfather was in diapers. And when the Romans finally fell into decline, the golden age of Islam was just about ready to begin, and the golden age of India had begun already. So we can go back there. You watch the patterns. The stars will be called different things in different constellations, but someone will notice the last time it was around, and they'll describe it exactly where you see it now. So yeah.
But like, would they be considered to be in an inertial frame of reference?
Oh, that's what we're talking about on Monday. Hold that thought. All right, I want to take a quick look at what people have simplified so far. I think the most don't round and simplify your you need to what you do with omega is constructed upon T is what you get from the astronomers.
Oh,
You had previous that are.
yeah, I just thought so.
Okay. All right, Eliana, what do you have for Kepler's third law?
4 pi squared r cubed divided by t squared big G.
Okay. There is Kepler's third law rearranged to solve for mass. If you want to measure the mass of anything in the sky, what two things could the astronomers give you that would enable you to measure the mass of anything you can see?
The radius?
And what would the radius literally be in this case? What does R mean for this?
The distance between the center of the galaxy and the
Okay, the distance between the center of the galaxy and whatever it is you're measuring. It could be the radius of the star, which would be the diameter cut in half, or it could be the radius of the galaxy. All right, what's the other thing you need to? The period. And we've just discovered that you've got 3,000 years worth of astronomical data, so that it's simply a matter of research. You may not even need to find it personally. This is how we can measure the mass of galaxies without putting it on a scale. And I wanted to start with the Newtonian physics to make it absolutely clear. We've been doing this for 400 years. This method works, and it's brilliant And it doesn't involve anybody trying to put a bathroom scale under the sun and then being surprised when the scale vaporizes due to the heat. Now, let's take it from there. Can we verify these 300-year-old calculations and confirm the mass of the star? How do we really know the mass of the star? Modern astronomers don't try to measure the radius of a galaxy. You can tell the mass of the star based on its luminosity. Stars are mainly made of hydrogen. You'll be listening to this for homework when you listen to the life cycle of a star and how a black hole is made. The hydrogen is there as fuel. Stars are giant nuclear fusion factories. Most of what they're doing is fusing hydrogen into helium. That's where the heat and light come from. If the star has more fuel, it's going to be fusing more hydrogen. It will have more fusion, it will have more energy, it will be hotter and brighter. So for the past few centuries, we've been comparing other stars' luminosity to our sun's, and we can calculate how much more or less massive the other stars are based on whether they're just as bright as our sun, 10 times as bright as the sun, 100 times as bright as the sun, all the way up. You can see that although the function has fractions and weird exponential powers, this section of the graph that is near to our sun, 100 times smaller to 10,000 times bigger, looks practically linear. The heavier star is, the brighter it is. Flip it around, the brighter the star is in the sky, the more massive it is. We've independently verified these mass calculations. We've got Newtonian orbits, and we've got what the chemists tell us about luminosity and nuclear fusion. They all agree. We can measure the mass of stars and galaxies 2 different ways and get the same thing every time. Now, measuring R, that's going to be a little more complicated. This is where we go back to the 1600s when all this was called natural philosophy, where geometry, trigonometry, and astronomy were all in the same department at the university. It's called stellar parallax, and it's basically geometry in space with similar triangles. Arik, you were really onto something when you asked, how do we measure the period? I know what the period of the Earth is. It's 1 year. And that means precisely 6 months from now, if I was over here now, 6 months from now, I'm going to be over here. It stands to reason. Our orbit is so has such low eccentricity, it's practically circular. And that means the distance between November, December, January, February, March, April, May, the distance between now and next May is 2 astronomical units. What's an astronomical unit? It's the distance from the Earth to the sun. I love it. You don't need meters. It's just like one of those things we can see. Now, make the measurement of where the star is, what angle of the sky you have to look to in November. Make it again in May, and you'll have a beautiful set of similar triangles with a perpendicular bisector. Sorry about that. Make that darn thing go away. There we go. So you point your radio telescope, you adjust the angle 6 months later. See how the similar triangles go? You can do a star, you can do a star cluster, you can do a galaxy, but the distance is going to be the reciprocal of what's called the parallax angle. Thank you very much for working out the units. And then we have a lovely, lovely geometry problem. D, that's our hypotenuse. That's the reciprocal of the parallax angle in these lovely units. Theta, we got from the angle we had to tilt our radio telescope from November until May. That's a right angle. This is SOHCAHTOA here. We can get R, which is what we were after for finding the speed. We can even get D, the distance between us and the center of the galaxy, just by looking at the star. Well done on those mathematicians. Now, We said the whole point of this was to look at the velocity. We said we can do this by Newtonian gravity. We can independently verify the mass because of the brightness of the star. We can independently verify the distance because of parallax, basic geometry, and trig. We can also independently confirm the velocity of the star based on its Doppler shift. So thank you very much, Jonah, for doing the physics spotting video on this back in August. Let's review what that looks like if the wave source is moving.
Isn't the Doppler effect when you like can't hear trains?
Yes, because the sound waves are all bunched up like
The same
this.
direction as the source become closer and closer, while the wavefronts in the opposite direction of the source become more spread out.
Couldn't have put it better myself. If the object is moving toward you at almost light speeds, the math becomes very complicated. But as you can see, the waves bunch up in the front. That's going to look more violet and blue, and the waves spread out in the back. That's going to look more orange and red. The fact that stars are mostly made of hydrogen means that this ceases being a physics problem or a chemistry problem, and it becomes a simple arithmetic problem. This is what hydrogen looks like. Here's the spectrum. You shine a light through the hydrogen, you're going to see some absorption lines here, 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 and here, and that's how you know it's hydrogen. Chemists use this to test all the time. Now take a look at the star. We have to 8 sig figs the absorption spectrum of hydrogen. It's here. If you see a star whose, take a look, the spacing is the same, but everything is shifted toward the blue end, that star is moving toward us. The wavelengths got bunched up on their way to Earth because the star was coming toward us as it emitted the waves. If you see the same spacing, but it's shifted several nanometers or several dozen nanometers toward the red end of the spectrum, that star must be moving away from us. And thanks to the equation for relativistic Doppler effect, greatly simplified, if you can see the amount of change that a very poorly paid graduate student could freaking measure with a ruler if it were big enough, divided by the actual wavelength that you're working on, which you knew already because it was there in the chemistry index for you, you can calculate the exact speed of the star, and you can verify the calculation that you did based on Newtonian mechanics. And it will agree every time because physics is physics and your numbers are still right. This works. This works. This works. One small problem. They don't work. 1965, the old boys club at the Palomar Observatory finally agrees that the brilliant and talented Vera Rubin can actually show up and do science because she's awesome. Now, there's such an old boys club that they let her in the front door. They forgot that nobody ever built a ladies' room. Vera Rubin cut out a white triangle out of paper, taped it onto the door, and said, "There," points to sign, slightly altered. Now you have a ladies' room. Male astronomers felt silly. Vera Rubin got on with her work. She was watching the Andromeda galaxy. How fast should stars on the outer edge of the Andromeda galaxy be traveling as compared to the inner ones? Take a look at the formula. If R is bigger, what should happen to V?
Really smaller.
The stars on the outer rim should be traveling much slower than the stars inside with a small denominator. So it stands to reason. It's basic algebra. Problem is they don't. Stars far away from the center travel as fast as those near the center. That's crazy. The denominator is bigger. What would have to be true in order for this V basically not to change? Yes, the numerator would have to be different. The numerator would have to be more. What? But it isn't. We can see the mass with our own eyes. It's a star. It glows. Vera Rubin was not there to shake the tree. She'd already become the first woman in North America to be allowed into Palomar. She was diffident. She was quiet. She was, dare I say it, very feminine about this. She didn't want to make waves and make trouble. She just went on taking data, and anybody who wanted to see could see. And by the 1970s, she had, without any fuss whatsoever, gained a huge following of people looking at other galaxies saying, this is impossible. We've verified this formula 3 different ways. Why isn't it working? Dozens more galaxies, whole galaxy clusters, were orbiting way, way faster than they ought to. And by 1970s, everybody knows that Vera Rubin has discovered dark matter. Those of you who read his dark materials, Philip Pullman didn't invent it. Duncan Matily was Swiss scientist Fritz Zwicky's discussion, his hypothesis about invisible mass in a giant numerator, because he first noticed this phenomenon in 1933. He noticed it for one tiny corner of the universe. No one paid much attention until Vera Rubin experimentally verified that this was absolutely right. It was happening everywhere. Here's what we can see. Optical telescope. Here's the model that we get from the Chandra X-ray telescope about where the mass would have to be in order for the speeds that we see at the edges of galaxies actually to be true. Something other than the visible mass is responsible for all the motions of all those stars. It has to be. There's no other way. We've verified that formula 3 different ways, and we've verified the data. The only possible solution is that that numerator has to be bigger. So in addition to the stars that we can see, there is a cloud of mass that we can't see, we can't touch, we can't feel, we can't sense. But as you can see, there's quite a lot of it. And that mass contributes to the n in the square root of gm over r, which explains why the stars are not going as slow as we expect them to. Yes, they're further away from the galactic center mass, but apparently they're closer to this big cloud of invisible. Yes.
If the dark matter is sensible and stable, how did they discover it?
The velocity. It's the only solution to the mathematical equation.
So like no one actually knows.
It's really there, all right. You give me a good reason why when you double the r in the denominator, nothing happens to the v. It's the only solution. We've verified it 3 different ways. You verified it yourself in the algebra problems you did at the beginning of class, the chemistry with the emission spectra, and the physics with the Doppler effect. All agree. There's no other solution. This is the dark matter halo. It extends way beyond the part of the galaxy that we can see, and that's why it's so powerful in the numerator. You're nowhere near the edge of the dark matter when you're near the edge of the galaxy. And that dark matter contains 5 to 10 times as much mass as the galaxy we can see, which explains why no one cares whether you are near or far from the center of the galaxy, because you're nowhere near the edge of that enormous cloud of dark matter. Dark matter outnumbers regular matter by a good 6 to 1. That means it is 85% of our universe. It's completely colorless. It has no electric charge. We can't touch it. We can't see it. It's got us beat by 6 to 1. So how do we know it's there? Well, this is what the velocity should be doing. This is what the velocity is actually doing. There's no other solution.
Wait, Ms. Eliezer, could you go back 1 slide?
Sure.
Okay, thank you.
And this is where we're going to go on Monday. We can't see the dark matter, but we can see the optical illusions caused by lots of mass on a big scale of space. Take a look at this picture, which has not been photoshopped. Do you see what looks like scratched swirls in the camera lens? Do you see the circular patterns? Okay, if you see this without your glasses, as I'll say in the lecture over the weekend, check with your optometrist. That is not healthy. That's a scratch lens if I ever saw one. The problem is our lenses weren't scratched. Something in there has floated across our field of vision like a giant invisible lens. And we're going to discuss in the lecture over the weekend and on Monday how it is that mass can do that. This is dark matter in action. It acts like any other mass in terms of distorting our field of view across space. Now let's move into the 1990s and the 2000s. The Wilkinson microwave anisotropy probe that is there to measure cosmic background radiation. Here it is. This is the cosmic microwave background radiation, CMBR. It is literally the last light of creation fossilized in time. This is the energy pattern in the universe, the instant before the universe became transparent. When hydrogen was invented. Read about it in Weinberg's The First 3 Minutes. We're towards the end of the 3rd minute. When hydrogen becomes transparent, those photons of microwave take off in all directions. They can now go through the universe because the universe is transparent. They're still there now. They're redshifted like anything, but they're still there. And when we look at that picture of the universe as it was 13.77 billion years minus about 5 minutes ago, we'll see that the patterns there do not correspond to the patterns of mass as we know it now. We're zooming in backwards in time. This grew into that. You can see the splotches where the mass is now. You could see where the galaxy, you could see that then the seeds of the galaxies that are now. Problem is, if you look at the graphs, this is a graph of what we have now. Temperature as relates to energy, as relates to the microwaves. It's the right pattern, it's in the wrong place. Now, again, do the same math correction. Say there's a huge cloud of invisible, untouchable mass right here that's going to left shift the energy pattern by several hundred, and you get what WMAP showed us. WMAP confirms that as far as the temperature and the energy readings go, something is mediating all that thermal energy exactly where the mathematicians say it ought to be. What's more, they noticed that that cloud is not uniform. This is an artist rendition based on the map, but it's pretty standard to color code dark matter with blue. Do you see how it's clumped around the stars and galaxies, but it's not actually uniform? Dark matter came from the Big Bang with the rest of us. The seeds of those dark matter clouds are there. You can see them in the microwave background. It's not isotropic, it's not homogeneous, and it grew. Go back in time, the distribution of dark matter was not the same any more than the distribution of our galaxies was the same. Dark matter, this news is about 2 years old, is organized by thermodynamic equilibrium. It's trying to come to equilibrium as far as its heat energy is concerned. What's the optimizing factor? Entropy. You studied entropy in chemistry last year before the schools closed. So it is as random as possible while allowing for uniform heat flow. So it's clumped around the stars, but not in nice uniform clumps that you can shade with a pencil. Now, this was a great day in the 21st century dark physics when they did the math and they figured out where the dark matter was here. This is 2 galaxy clusters colliding. Ladies and gentlemen, a galaxy cluster is several dozen or several hundred galaxies. If you stick your finger right in the middle of it, what are you likely to touch? And other stupid questions. Several hundred galaxies, you stick your finger in the middle, what are you going to hit? Really, are you likely to hit a star, statistically speaking? No, what are you likely to hit? You're likely to hit a big patch of nothing with several 100,000 stars, several parsecs all around. Galaxies, ladies and gentlemen, are mostly empty space, except for those bits where they're not. If you collide 2 galaxy clusters, they're going to pass right through each other because they're mostly empty space. Maybe there will be 5 or 6 really unlucky stars that go boom, but most of them aren't even going to know that the other is there. Matter galaxies are mostly made of stars with a lot of empty space in the middle. But dark matter does not collect into dark stars or dark planets or dark anything. It's a cloud, and those 2 clouds are not mostly empty space, they're mostly dark matter. And they collide like anything. Can you see the shock wave? soundtrack here, I think, is unnecessarily dramatic. Here's the map. Can you see the shock wave as the cloud moves toward the other one at speed and collides with it head on? Let's watch it again. One dark matter cloud, the other dark matter cloud, bam. This is called the bullet cluster. Can you see the shock wave as the dark matter is blown away from the collision? You see the wavefront here? There is a cloud of something there, and that cloud has fully been smacked. It was traveling at speed, exactly like those waves in the bowl that Jonah was making. And you can see stuff bunching up in front of it and spreading out behind it. Dark matter is real. So what's the deal? Luminous matter, also known as matter, interacts with electromagnetism. I can't stick my fingers through it. Technically it's mostly empty space, but it's there. Why? It has electric charge. The fact that you can't stick your fingers through your own desk comes down to the fact that you have electrons and so does the desk, and they do not like each other. They repel. It's much more complicated than that on the subatomic scale. There are lots of, we're going to learn about virtual photon exchanges in May, but the buck stops at electromagnetism. Matter responds to magnetic fields. If it's the right kind of matter, you can stick things to the fridge on it or with it. Matter absorbs and emits light, which is why we can see it. We see the light scattering off it. We can process the light scattering off it. That's why it has color. And frankly, given that we're talking about stars, I don't think anybody is going to argue about the fact that ordinary stars glow. That's what they do. That's how we know they're there. It comes down to electromagnetism. We also know they're there because we happen to be orbiting a very large one, and it gives us these things we call seasons. We have gravity. The sun has mass. That's why we're here. The sun has weight, which is why you shouldn't get too close to it in your spaceship unless you feel like spending your next life as Kentucky Fried Chicken. It has inertia. It travels through the galaxy. It orbits other mass. Our sun is orbiting the galactic center, same as everybody else. And as we're going to learn over the weekend on Monday, it affects the space-time continuum. Dark matter. Compare, contrast. Dark matter is completely immune to electromagnetism. It couldn't care less about photons. It doesn't process them, it doesn't collect them, it doesn't exchange them, it doesn't trade them. And because it's completely immune to electromagnetism, it can't be felt, it can't be touched. We stick our fingers through them, its fingers don't care. It can't be seen because it doesn't interact with light or process or any way. It has no texture, it has no color, it has no temperature because it doesn't affect the motion of matter. It doesn't glow in any fashion, but it does interact with gravity. It's got mass, it's got weight, it's got inertia. Frankly, if we use those wave motion properties that predict shock waves, it behaves the same as anything else that's just come in a cloud and hit something smack on. It orbits other mass like galactic centers, and yes, it affects the space-time continuum. Hassan posted this on my Facebook feed when I was checking my facts with the professors. Hassan can find an XKCD for anything. Yes, there's quite a lot of dark matter in the solar system. As far as scales go, it means in the neighborhood of this planet, we have approximately 1 squirrel's worth of dark matter. But no, it's not that squirrel over there. It's just a metaphor. Even though we can't see it, we can't feel it, we can't touch it, dark matter is most definitely there. The math is absolutely clear. We should feel very proud of ourselves. The fact is, galaxies spin way too fast. We've got more than 100 years worth of data. We're pushing a 100-year anniversary of somebody saying galaxies spin way too fast. Between the heat and the speed, they should have torn themselves apart long ago. The Milky Way is old. We should not still be in the western spiral arm of the Milky Way. We should have been flung off like every water bucket demonstration gone wrong. Galaxies cluster in groups. Yes, mass, gravity, boom. But they cluster around something we can't see. We can see the galactic center. We know we're spiraling around the Milky Way. But the Milky Way and the Andromeda Galaxy and many others are clustered and they're orbiting around something we can't see. Newton says, I'm going to suggest that if we can't see it, it probably has mass because all these galaxies are orbiting it. Einstein says, Newton, love you forever, but you missed a few things that you couldn't see from a telescope in the 1680s. The mass distorts space-time. You're going to see weird optical effects if you look far enough into space in the neighborhood of really big mass. Einstein says dark matter does this too. We've explained it all. It's consistent with every theory of gravity that's ever been put forward from 1685 to 2020. Here are some of the nicest looking dark matter charts that are part of the public purview. You can see the stars, you can see the galaxies, and you can see that here and here, there's a whole lot of dark matter, even though there isn't much in the way of stars. This is what we mean when we say dark matter outweighs regular matter by 6 to 1. If you're looking at the matter and energy profile of the universe, dark matter has us thoroughly thrashed. It's a quarter of what's out there. This is the graphic that I got from the Perimeter Institute, the same one I got your lab from. This is one model of dark matter clumps in a certain neighborhood of a certain galaxy. This is what I mean when I say it's not uniform. It's clumpy like any other nebula in outer space with gas and dust and schmutz and the occasional asteroid here and there. And these clouds spin and move, and yes, they occasionally blow away in the force of some shockwave or some explosion, just like regular nebulas. The difference is they don't glow, so we can't see them. Now, 2020. This is the cutting edge of modern physics. Things I can't tell you. We have answered a lot of questions. We have discovered a few more. You asked me what dark matter is made of. I have not the faintest idea. For almost 20 years, we've been talking about weakly interacting massive particles, called WIMPS for short. Yeah, I was looking for 2020 data on WIMPS. I found a conference abstract from 2018, which was 2 years ago, saying the team reporting to the international community about the search for WIMPS sounded almost apologetic as they presented their complete lack of conclusions, evidence, or any progress on this in the past 15 years. The writer of the abstract was not impressed and said, maybe the reason you haven't made any progress on this experiment in 15 years is because it's not there. That's why you can't find it. There are a whole bunch of theories as to what dark matter is made of. I thought this was a particularly good graphic in explaining just how well they work and how much we've proved any of them. Supersymmetric particles. This was the one that even predated the existence of dark matter. The idea of supersymmetry, that everything lines up. Yeah, the last really good paper I saw on that had publication date of 2007. That's 13 years ago. I'm going on the theory if they haven't made any progress in 13 years, that might be because it's not there either. What is dark matter made of? I give y'all 5 years for an undergraduate degree, 8 years for a graduate degree. You come back and tell me. I'll be really excited to see what you find. Now, speaking of supersymmetry and other things we haven't found yet, why isn't there a universe made out of dark matter with dark stars and dark galaxies and dark planets full of, dark doubles? The English department would have a field day of that. Well, one theory is that there is. It's called Hidden Valley theory. It's out there somewhere. They're working on that now. The other theory is that universe is right here. It's a universe of low mass interactions. This concludes Dark Matter Day, ladies and gentlemen. Enjoy your black holes over the weekend, and I will see you on Monday for gravitational lensing, general relativity, and the wide world of Einstein.
Mrs. Eliezer. Just to clarify, our homework is the notes on black holes part 1, black holes part 2, and answer the questions.
Yes, they're designed to be very, very short questions.
Awesome. Thank you.
Okay. Which one was it?
I was saying that I was thinking about there could be a
Oh, there's some point when there's some point.
Yes. My pleasure. Thank you, Ms.